Good morning, all of you. Welcome to physics online session. So, this is our chapter. Now, we are discussing ray optics and optical instrument chapter. So, in the first half of this chapter, we have discussed some phenomena, reflection of light, refraction, total internal reflection, dispersion. By using these phenomena, so some optical devices are designed. They are mirrors, lenses, prisms. Okay, so periscopes, microscope and telescope. In the following classes we will discuss some of the optical devices like microscopes and telescope, and we have discussed the mirrors, lenses and prisms in the previous classes. Okay, now our human eye is also one of the most important optical device that nature given to us. Okay, now in this class we'll discuss the structure and working of a human eye, and defects that arises in the vision of a human eye. Okay, and their correction also. In the next classes we will discuss the principle and working of microscope and telescopes. Okay, now I'll start with the human eye now. Okay, so here see the structure of human eye. It is almost in a spherical shape. It is in a spherical shape. That but the front portion is sharply curved. Okay, human eye is the most important sense organ. It's an important organ of a human body. Okay, sense organ, and these are the different parts of eye. The front portion, so this front portion is called, the front portion which is sharply curved is known as cornea. So light enters the eye through this cornea. Okay, so and behind this cornea there is a pupil. Okay, so pupil at the center of iris. Okay, so this is iris. So at the center of this there is a central hole in the eye, in the iris, that is called the pupil. Okay, through which light passes incident on the lens. This iris helps the pupil to expand and contracts in the low and dull light conditions. When the light is under dull light conditions or low light conditions, what we do, will expand our eyes. Okay, so this can be done by iris. Iris helps the pupil to expand under dull light conditions, so that we can see the objects comfortable clearly. Okay, but in high light conditions, bright light conditions, so it restricts the amount of light that is passing through the pupil. So uh, in that case iris contracts or compress the pupil, so that only uh, needful light passes through the eye lens. Okay, this is a working of iris. Okay, and the next one, and through this pupil light falls on the lens. So this is called eye lens. This eye lens forms the image on the, it forms the image on the retina, forms the image of any object in front of the eye on the retina. It is used to form the image on the retina. Okay, and 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 what about retina? Retina contains a number of nerves. it has 125 million nerves, and there are two types of nerves are rods and cones. Rods identify color and cones identify intensity of light. Okay, and whatever the light incident on the retina is transmitted to the brain with the help of this optic nerve. It contains 1 million nerves, optic nerves. So a brain uh, interpret the signals, and so that we can understand the uh, light or the object. Okay, so and here the distance between the eye lens and the retina is fixed. It is about 2.5 centimeters. This distance is fixed. Okay, whatever the position of the object, the image is formed on the retina. So the image distance is fixed here. Okay, so look at uh, the lens equation. Since there is a lens, so lens formula 1 by f equals to 1 by v minus 1 by u. Okay, here u, so for any position of the object, image distance is constant. V is constant here. This distance cannot change. It is fixed. Okay, so if u changes, then definitely focal length has to change. Okay, so then only it forms the image on the retina. Okay, so what is happening to the focal length here? Focal length of the eye lens is changing. Okay, so eye lens has to change its focal length so that it forms the image on the retina. Okay, so this can be done by ciliary muscle. So where is this is a ciliary muscle. So this ciliary muscle uh, so helps the eye lens to change its focal length. So this property of adjusting the focal length of eye lens is called as accommodation. The property of adjusting the focal length is known as accommodation. This accommodation can be done with the help of a ciliary muscle. For example, when you are focusing the distant object, for example, eye lens is focusing the distant object, long distance object at infinity, our eyes feel relaxed, so that when object is at infinity, since v is constant, so where the image will be focused on the at the focus. So that is 1 by f is equals to 1 by v minus 1 by u. Since u equals to infinity, v equals to f. Okay, so focal length is equals to image distance. So image is formed on the retina. Here eye lens, no need to adjust its focal length. No, I feel relaxed. Why? Because no need to adjust the focal length here. Okay. Now when eye lens is focusing the nearby objects, okay, so nearby object, it has to adjust its focal length so that image forms on the retina. Okay, why? Because whenever the object distance changes, so since the image distance is constant, so definitely its focal length has to change. Okay, when you are focusing the nearby objects, okay, so this ciliary muscle helps the lens to compress, shrinks, so the focal length decreases, and so that the image forms on the retina. Okay, so that we can see the objects clearly and distinctly. So but there is a limit for the accommodation. It doesn't form the clear image of an object for all object distances. For example, This is a eye lens. If the object is at 25 centimeters or more than 25 centimeters, we can see the objects clearly and distinctly for a healthy eye. For normal eye, if objects are placed at 25 centimeters and above 25 centimeters, we can see them clearly and distinctly without any strain. Okay, so the distance, this distance is called least distance of distinct vision, least distance of distinct vision, or this is a minimum distance for clear vision without any strain. If the object is placed below this distance, so this eye lens cannot adjust its focal length. Okay, so therefore our eyes feel strained to view close objects. Okay, so this distance is called least distance of distinct vision, and it is also called as near point. Near point, if the distance object is below the near point, so we cannot see the object uh, without strain and clearly and distinctly. Okay, so this is about the structure and working of human eye. Okay, so with the aging ciliary, this ciliary muscle weakens. Okay, so it loses the property of accommodation, so it cannot adjust its focal length after a certain age. Okay, or there are also certain reasons for the failure of accommodation in the smaller uh, ages only. Okay, because of some reasons, so this ciliary muscle weakens and it loses the property of accommodation. That is why we'll get certain defects in the vision. So they are myopia. First one is myopia and hypermetropia. So there is also presbyopia and astigmatism. These are certain defects in the vision of human eye. Okay, first we will discuss what is myopia. So myopia, it is called as nearsightedness, short or nearsightedness. The person who is suffering from myopia can see only the nearby objects clearly but cannot see the distant objects clearly. So that is why it is known as short sightedness. He can only see the nearby objects clearly, so that the defect is known as nearsightedness. Okay, so and okay, so this is, we'll discuss this point later. And the myopic eye forms the image of distant object before the retina. Okay, you can see the this is a normal eye without any defect. Normal eye, there is no defect, with no defect, sorry, with no defect. So normal eye, no defect in the vision. So what happens, uh, even though actually it is a for myopic eye, not a normal eye. For normal eye, it is not represented here in this case. Okay, so for normal eye, even though the object is at infinity, it forms the image on the retina for normal eye, in case of normal eye. But in case of myopic eye, the far point, so for normal eye, far point is at infinity, even though the object is at a long distance, infinite nothing but a distant object. Okay, so light rays almost parallel when object is at infinity. So even though the object is at infinity, it forms the image correctly on the retina. Okay, so we can see that object clearly and distinctly. For but for the person who is suffering from myopia cannot see this distant object. Why? Because the light rays which are coming from distant object are not focusing on the retina, so they are focusing before, just before the retina, so that he cannot see the object clearly and distinctly. So okay, so whenever the light rays falls under the retina exactly, then only the person can see that object clearly. But the light rays which are coming from distant object are not focusing on the retina, so he will see the blurred image of that object. Okay, so uh, but uh, this person who is suffering from myopia can see the object clearly and distinctly, so up to certain distance. Okay, if you place an object beyond this distance, if you place an object here, okay, if a person is standing, any person is standing, so beyond this distance he cannot identify that person. Okay, so this is called a far point. Up to this distance only the person can see the object, okay, clearly. After this distance he cannot see that object clearly and distinctly. This is called far point. For normal eye the focal length is infinity. For a myopic eye it is smaller than the infinity. That is why this point, that is the meaning of this point. For hypermetropic eye, this one is in this defect, the near, sorry, okay, that is why um, far point is closer than the infinity. This far point is closer than the infinity. This is the far point. Sometimes it is also present with m, far point, and distance is d. Okay, so yeah, if object is, for myopic eye, if object is placed between the far point and near point, near point, you know what is the near point? It is the 25 centimeter. If the object is in between uh, 25 centimeters and far point, then only n and o is o or m is a far point, n is a near point. If object is placed between m and n, then only he can see the person, then only he can see the object clearly and distinctly. Okay, so and how can you correct this myopia? So this myopia can be corrected by using a biconcave lens. So it is a diverging lens. Okay, so now we are focusing a distant object. Now I want to see the distant object with the help of some any optical device. Now we are taking a biconcave lens. This is a biconcave lens. Okay, since it is a diverging lens, so light rays after passing through this lens, so diverges, okay, not converges. If this is a parallel beam of light, if light rays after passing through the convex lens, it converges actually. After passing through a concave lens, it appears slightly diverges. Okay, so diverges. So here what happens, the light rays after passing through the concave lens slightly diverges, so it diverges slightly. So there is a, we are placing the concave lens so that slightly diverges, so exactly focus, uh, so the light rays after passing through this lens, so exactly focus on the retina. But these light rays uh, appears to be coming from o. Okay, so here uh, so what this convex lens is doing, concave lens is doing, this biconcave lens forms the image, forms the image of distant distant object uh, at near, at far point or below, below the far point, below the far point. Okay, so it will bring the object um, from infinity to a far point. So when for islands, so what I feels, so object is not coming from the infinity, it is coming from a far point. So when an object is at far point, so these islands can see that object clearly and distinctly. So in this way we can correct myopia. Okay, right. So and we'll find a expression for focal length of this biconcave lens. What is the focal length? Required focal length. Okay, so what is this distance? This is the far point. Let us represent with a D. Okay, so so for this for biconcave biconcave lens, where the object is located, object is at infinity. Okay, so this is the lens, so and object is at infinity, u is equals to minus infinity. Why? Because light rays are moving towards right and we are measuring distance from the pole. So okay, so object distance is negative. And what about the image distance? So this biconcave lens forms the image, so the virtual image, not the real image, it forms a virtual image on the same side. Okay, so at what distance? So let this distance d, far point. Okay, the image is formed at the far point, let us suppose. So this distance also measured opposite to the direction of incident light, so it is taken as negative. Okay, so what is the focal length? Okay, we use lens formula, that is 1 by f is equals to 1 by v minus 1 by u. So that implies 1 by f is equals to 1 by minus d minus 1 by minus infinity. What do you get finally? F is equals to minus d. What is the focal length of uh, this biconcave lens? It must be equals to near point. We got negative. Why? Because since it is a biconcave lens, focal length of the biconcave lens should be negative. Okay, so this is the required focal length. It depends upon the far point of the person. Okay, in this way we can correct myopia. Okay, and then what about hypermetropia? So hypermetropia is called far sightedness or long sightedness. Why? Because the person can only see the long distance object clearly but cannot see the nearby objects clearly and distinctly. Okay, in this defect the near point is greater than infinity. So we'll discuss this point later. So hypermetropic eye forms the image of nearby object behind the retina. You can see the image. So here right. Okay, so here near point of hypermetropic eye. So hypermetropic eye, here image is formed behind the retina. So okay, when object formed behind the retina, the person cannot see the object clearly and distinctly. Okay, so what about the near point generally? So the near point, actual near point is near n equals to 25 centimeter. But person who is suffering from hypermetropia, their near point is not, it is greater than 25 centimeter. That is why in this defect near point is greater than it is wrong, it is greater than 25 centimeters. Okay, okay, for normal eye the near point is 25 centimeter, and for children the near point is about 7 to 8 centimeters. And with the aging, as the accommodation of islands weakens, so for old people it is about 2 to 3 meters, 3 meter 200 to 300 centimeters. This is the least distance for distinct vision or near point for the old people. Okay, for children it is very, they can see nearby objects, closer objects very clearly and distinctly. Their accommodation is very good. Okay, no, that is why in this case a person who is suffering from hypermetropia cannot see the object which is placed at 25 centimeter near point. Okay, why? Because for older people it is about 200 to 300 centimeter. If the object is placed after 200 centimeter, after 1 meter or 2 meter, then only those person can see that object clearly and distinctly. But if you place an object at 25 centimeter, the person cannot see. That is why we can say that for hypermetropic eye, the near point is more than the 25 centimeter. It is 200, but definitely it is greater than 25 centimeter. So hypermetropic eye forms the image behind the retina. Okay, that is why the person cannot see the object clearly and distinctly. So this defect is corrected by using biconvex lens or converging lens. Okay, this is a near point of a person who is suffering from hypermetropia. It is, so n is greater than 25 centimeters here. Okay, for the person is greater than suffering from hypermetropia. Now what when you place an object at 25 centimeters, so what happens here? So definitely, so eye lens does not adjust its ciliary muscle does not adjust its focal length, so it forms the image somewhere some other place. Okay, not on the retina, so it is actually behind the retina. So how can you correct this defect? So by using a biconvex lens. Okay, when you place a convex lens, what happens here? Light rays, if you place a convex lens, what happens to the light rays? It converges. Since the convex lens is converging, so it converges the light rays. So if you place a convex lens here, since it is a converging lens, it converges the light rays. So all these light rays after passing through this lens, so will come to focus at this point. In this way we can correct what hypermetropia. Okay, right. So what it will do, it forms when you are placing an object. Actually we are placing a textbook or any object at a 25 centimeter normal near point, but the person cannot see without any optical device. But when you place a convex lens, what happens? This convex lens forms the image of this object. uh, so it For example, a person who is suffering from hypermetropia have near point of 200 centimeters. So when you place an object at 25 centimeters, so this convex lens forms the image of the object at 200 centimeters on the same side. Okay, so what I feel, so the object is not coming from 25 centimeter, it appears to be coming from 200 centimeter. The light rays from that object are coming from 200 centimeter, so he can see the object clearly and distinctly. Why? Because light rays coming to focus at this point on the retina. Now we'll derive an expression for focal length, that is what should be the focal length of the convex lens, so we can correct hypermetropia. So this is the near point. This is the near point. In this case also I want to represent with d. D is the near point distance. Okay, now what is the lens formula? We use lens formula to find it. 1 by f equals to 1 by v minus 1 by u. Where the object is located, so where we are placing an object here at normal near point 25 centimeters. It is on the left side, so measured opposite to the direction of incident light, so it is taken as negative minus 25 centimeters. So when image is what about the image distance? Where the image is formed at a distance d. Okay, it is the near point of hypermetropic eye. N dash is the normal near point here. Okay, so it is taken like that. N dash is nothing but a normal near point. Okay, where the object is located at 25 centimeter, normal near point. But what is the near point of hypermetropic person? And about to 200 or 100, whatever it is, more than 25 centimeters. And image is formed on the near point. Okay, which is about around, which is greater than 200, which is greater than 25 centimeters. V equals to minus d. Why? Because it is also measured opposite to the direction of incident light. So okay, this convex lens forms the image of the object at 25 centimeter, image of the object which is at 25 centimeter at d distance, so that person can see the object clearly and distinctly. Our aim is to find out the focal length. 1 by f equals to 1 by v. What is v? Minus d minus 1 by minus 25 centimeter. We will get 1 by f is equals to this is plus 1 by 25 minus 1 by d, and what we get, 1 by f is equals to uh, d minus 25 by 25d. So therefore f is equals to 25d by d minus 25. So by using this formula, if you know the near point of a person who is suffering from normal hypermetropia, you can easily find the focal length required to correct this defect. Okay, so there is another defect, that is astigmatism. Okay, so here in this case, when object, a square like object, a mesh wire like object, when placed before the eye lens, it forms the image on the exactly on the retina, but the shape of this object is distorted. Okay, we are not going to uh, discuss detail about this defect. So here in this case, what happens in this case, in case of astigmatism, here the shape of the object changes here. Okay, but you can see it clearly, but shape of the object it changes. Actual object is like this. You can see drum, take, or pin cushion object like this. Okay, and this can be corrected by using a cylindrical lens. Okay, so this can be corrected by using cylindrical lens. Myopia can be corrected by using a biconcave lens. Hypermetropia can be corrected by using biconvex lens. There is a presbyopia. Okay, person with aging, so we'll get presbyopia. Presbyopia is a combination of uh, myopia and hypermetropia. So to correct presbyopia, we need a bifocal lens. Means it is a combination of convex and concave. And for the correction of astigmatism, we need a cylindrical lens, nothing but a toric lens. Okay. So in the next class, so we'll discuss the principle and working of what microscope and telescope. Okay, this is about the structure in the what we have discussed in this class, structure of a human eye and working of different parts of a human eye. Okay, and defects that arises in the vision of human eye, so myopia, hypermetropia, and astigmatism, and how to correct them. Okay, thank you.